ball. Now this time I'm going to do something something drastic. I'm going to throw this ball out or drop this ball from an aeroplane. So that's what I'm going to do. Okay, I'm going to stick my hand out of the window and drop the ball. So the ball starts falling. Now, of course, you can't really do that. You can't open a window of an aeroplane. Let's just imagine that anyway. So this ball falls. So this is the part where I drop it, release it. Okay. Then the ball falls. All right. As it falls, it goes faster and faster. Okay. So now, as the ball falls with a certain velocity, I'll call that v. Okay, I'll call that v. Now the ball falls because there's this weight. All right, there's a weight pulling it down. Okay, the weight is a force that pulls the ball down. But as the ball falls faster and faster, there would be air resistance. Okay, there would be air resistance. Now the air resistance is an upward force. Is the force opposite to its motion, and so in this case it's pointing upwards. I'll call this resistance R. Okay. Now we can imagine that the faster it falls, the bigger R would be. Right. Now eventually, if it might fall so fast, since we are dropping it from an aeroplane, right? It's going to go so fast that, let's see, so fast what happens. So the weight doesn't change, right? Same ball, same earth, weight no change. Now it's from quite high up, but I'm going to assume that the weight is the same anyway, all the way up to the aircraft. Okay, we'll talk about how it can be different in a later topic on gravitation. But for now, we are going to imagine that when it falls really fast, right? And I'm talking about really, really fast. There comes a point when the resistance becomes bigger and bigger until, all right, at some point it must become as big as the weight. Now what happens then? Now when it becomes as big as the weight, the force from the resistance and the force from the weight cancel. Right? If they cancel, that means there's no more force. And if there's no more force, it won't accelerate anymore. Now we'll learn more about this later on in Newton's laws. But for now, please take my word for it that if the forces cancel, it can't accelerate. And if it can't accelerate anymore, the velocity is just going to stay the same. It won't go any faster because you need a force. Alright, you need a resultant force for something to accelerate. So no force, no acceleration, so the speed is going to be fixed. So it's just going to go, at the same speed from then on. Now there's a name for this speed that's going to stay the same all the way until it finally hits the ball finally hits the ground. This speed, you might have heard of this before, is called terminal velocity. Right, it's the final velocity that it reaches going through the air, and it doesn't increase anymore because of the air, because the air resistance balances the weights. So that's the idea about a falling object. Now, as we shall also learn later on, as the force decreases, acceleration also decreases. We learned that acceleration is directly related to force. So the moment the air resistance appears, it will cancel off some of the weights, right? And the acceleration would actually decrease, right? We have seen that acceleration due to gravity is 10 meters per second squared. So if there's no air resistance, I should be more precise here. I can afford to be more precise. It's 9.81 meters per second squared. Okay, so that's the acceleration. The velocity will increase by 9.81 meters per second every second. But that is only if there is no air resistance, or if the air resistance is really small. But because as it goes faster and faster, air resistance will actually get bigger and bigger. All right, it become a bigger and bigger part of the weight, fraction of the weight. So the resultant force becomes smaller and smaller. So therefore, the actual acceleration of the ball would actually also become smaller and smaller. So that's our description of this situation so far. All right. Next, I'm going to sketch some graphs to see what the velocity and acceleration look like, how they change with time. All right, that's the velocity axis, and that's the time axis. Now, as the ball falls, now this time I'm going to take v to be positive, so that I can have a graph up here where v is positive. So I'm just going to take the downward direction as positive this time. All right, since the velocity is going downwards. Now, so at first, when I first drop the ball from the aeroplane, if I take that to be my time t, the velocity at first is 0. So as time passes, the velocity increases, and it goes faster and faster and faster with time. All right, and eventually we know what happens. As I described, eventually when it reaches a certain terminal velocity where resistance balances the weight, it can't go any faster, it can't accelerate anymore. So from that point on, the velocity is going to stay fixed. So I know that after some time, I know that the velocity can't just keep going up. After some time, there's a limit. Let's see. Okay, there's a limit. Now I want to know what kind of shape this graph roughly look like. Okay, let me just think of something quite simplistic at first. Now, as I said, the velocity keeps going up, right? So can I just say that the velocity just keeps going up in a straight line until it hits this terminal velocity, and then after that it remains fixed like that? Is the graph going to look like that? Just one straight line until here, and then another straight line horizontally? Probably not, because if I have a straight line down here, that means that the acceleration is going to stay the same, right, over this stretch of time, because acceleration is the gradient of the velocity time graph, if you remember. But does the acceleration stay the same? Well, not really, because as we have seen, the resistance increases with time, so it cancels off more of the weight, and therefore acceleration should decrease. Okay, because the resultant force gets smaller and smaller. So that's not right. So what is more likely to be the case is that as time passes, the velocity, instead of going straight up, right, in a straight line, so it wouldn't go up in a straight line. Instead of that, it will the slope, all right, has to decrease because the acceleration decreases, the gradient decreases. So it will get more and more gentle, and then it will flatten off as it reaches the terminal velocity. So I get a curve, all right. So that's a more reasonable thing to expect. I actually get a curve down here. Now next, let me try and catch the acceleration time graph. So that's my A T graph, and we go back to the starting again when time is 0. So when time is 0, I'm here, and I know that when I just drop the ball, there's no air resistance. Air resistance only happens because of the motion, because of the velocity. So when I first drop the ball, the acceleration due to the gravity is just 9.81. Okay, there. So that's in meters per second squared, and in the beginning is 9.81. Now, as we have seen, the acceleration would decrease because of the increasing air resistance. So we can imagine that the acceleration, as time passes, decreases. Now, once again, we want to see what the graph looks like, and I'm going to ask the question: does the acceleration go straight down until the ball reaches terminal velocity, and then the acceleration becomes 0 after that, because the weight is balanced by the air resistance? Does it go straight? Right? Let's have a look at the velocity time graph. Now, if you recall, the gradient, if I take any point on the velocity time graph, the gradient at that point, that means the slope of this line here touching the curve there, the slope of the curve at that point, you see that the gradient gets more and more gentle. In other words, the gradient gets smaller and smaller. And since the gradient is just the acceleration in this velocity time graph, therefore we would expect the acceleration to get smaller and smaller as well. So it seems that, you know, having a straight line acceleration is not impossible. Okay, it's not impossible, and maybe at some point the acceleration reaches 0, and so the velocity, the slope of this graph reaches 0. But actually, alright, but we won't be able to tell without doing a proper mathematical calculation, which I shan't go into. So what I'm just going to say that actually the acceleration time graph would not be a straight line like this. So I'm going to just draw the answer. This is something we need to remember qualitatively for physics at this stage. The acceleration time graph, instead of going down in a straight line, it would curve. The slope, the slope will get more and more gentle, just like with the velocity time graph, right? Until it flattens out and gets very close to 0. So that's what the acceleration time graph would look like.